Right, people, here's the next lesson. This is going to be the last lesson for theory of elastic bending, I think. I did say in my previous one, I'm just going to give you a bit of a kickstart. Under the folder, I've put in an exercise called theory of elastic bending, further examples. Okay, there's it over there. Theory of elastic bending, further exercises. There's 6 or 7 bits in there. I'm going to just point out a few. First one there, pretty much there. Okay, it's the basic formula used is m over I is equal to f over y. I want to look at number 2, okay, which I've put in over there. Number 2 says that a universal beam spans 6 meters and carries a uniformly distributed load of that along its entire length. Right, I'm going to draw the picture. The picture looks something like so. Just quickly, it looks like so. Here's the UDL. UDL is equal to 50 kilonewton meters along its whole length, and it's a standard case. Okay, so you go to the beam formula, and you have to work out the formula for the maximum bending moment, which is in the middle. Or if you go to the standard case, or if you remember it, you will know what the formula is for the maximum bending moment at the center of a assembly supported beam with the UDL along its whole length, and the span is 6 meters, and the maximum moment at the center there, maybe I should say max bending moment max at center for a assembly supported beam is WL squared over 8. Okay, if you don't remember that, you'll have to work it out. You'll have to take moments to reactions and to all of that, but if you remember it, it's a lot quicker. Okay, so there's the UDL, there's the span, carries uniform. Says calculate the section modulus. Right, now section modulus, we know what it is. I'm going to state the formula. M over I is equal to F over Y. Theory of elastic bending. If I do some fancy manipulation here, you will see, okay, if you do the algebra, that M over F is equal to I over Y. Okay, if I manipulate positions of I and F, I get that over there. But what's I over Y equal to? I over Y is equal to, that's right, you remember, I'm sure, section modulus. There we go. I over Y is equal to Z, which is section modulus. So that means Z is also equal to the moment divided by the stress. Okay, right. Number A, let's just calculate the section modulus and design a suitable beam to adequately carry this load, assuming a maximum bending stress of that. So that there is F. So they've given us F, and yippee, we can work at the moment because they've given us that in the span. So now we can work out the section modular. Isn't that lovely? Yeah, the joy of analysis, isn't it? Right, so therefore M, I'm going to do it here, M is equal to 50 times the span squared over 8, which is equal to, and that gives me okay, it gives me 225, and it's a moment, kilonewton meters. Okay, right. And now be careful, kilonewton meters, millimeters, newtons. Be careful. People make this mistake all the time. I'm saying be careful. Right. F, and F is in newtons per millimeters. Okay, so therefore I'm going to say Z is equal to M over F, and M is equal to 225 times 10 to the power 6 Newton millimeters. You must know the conversion, and F is equal to 165, and if I work that out, okay, that's F over there, I get, what do I get? I get that to be 1.364 times 10 to the power 6. And what's the units for section modulus? Yes, millimeters cubed. There we go. Still the same. It's cubed. It's not the volume, but it's cubed. Right. Now, I'm going back to the question. It says calculate the section modulus, and now there's part A. Now we've done it. Part A is done. So the section modulus is 1.364 times 10 to the power 6 millimeter. There we go, lovely. There's the answer. We've done it. Okay, there's the answer. That's the answer I gave you there. Number B says determine a suitable beam to adequately carry this load, assuming that over there. Right. What you do is this. You go to the steel tables I gave you. Here's it over there. Remember that? Steel tables? Okay. And you go down to universal beams. That's universal beams. Okay, don't make a mistake. That's universal beams. That's universal columns. Get it right. That's the square section. Universal beam is the I section. Okay, right. You go to the tables and you look for the IXX and you look for Z elastic here. Can you see that there? About the XX axis Y, because bending is about the XX axis. And you go to the universal beam part of the table and you look for ZE under XX and you go down the table. Okay? And you go down the table and you look for a value. Are you with me? You look for a value that's equal to that or slightly larger than that, and you pick at that section. Okay, right. So I'm going to go down the table. But before we go down, just check this out. Look at the value there. These values there, this value, for example, is 27.8 times 10 to the power 3 millimeters cubed. And our value there is in 1.364 times 10 to the power 6 millimeters cubed. So can I compare this value with that value? No, I can't. I need to first get that into this over here. So that there is equal to 1364 times 10 to the power, yes, cube, millimeters cube. I needed to make this 1,000 times bigger, and I made it 1,000 times smaller. Okay, so notice that there. This now is this is 1364 times 10 to the power 3 millimeters cube. So this, I can compare this number with that number there, because this is all 27.8 times 10 to the power 3 millimeters cube. Did you get that? If you're not sure, go back and check it out again. So, what does the question say? Determine a suitable beam to adequately carry this load. So what you do is, once you converted this value to a value, you take this number 1364 and you go down the table under XXXZE for Z elastic, and you go down the table until you find a value that is equal to or slightly larger than that. So 1364, there we go. That's 1300, 1460. Okay? So what you do is, you go down the table under the Z elastic column and you look for a value that's equal to or slightly larger. And the one you want is that one over there. Okay, so the section we want is a 457 by 191 by 74 universal beam, because its Z elastic is slightly larger than that, so that means this beam will adequately carry the load. And there's the answer. That is how we get to that. Okay, so the beam you say, choose, therefore choose 457 by 191 by 74 kilograms per meter. Okay, I'm going back to the table there. And what's its Z elastic value? It is 1460. There's 1460. Okay, that is how we get that. And I put in brackets there. Z elastic is 1460 times 10 to the power 3 millimeters cube. And that's how we get to that whole answer there. Okay, so what I'll say it again. So what we do is, if you want to, and people, this is actually a little bit about beam design. This is how we design beam. This is a little bit of beam design. Okay, using the theory of elastic bending. We first find section modulus, which we did there, and convert it to a value so that it's times 10 to the power 3 millimeters cubed, and the value we get is 13464, or sorry, 1364. Then I go to the tables, and we go to the universal beam section, and I go to about XXZE column, and I keep going, and I keep going, and I look for a value that's equal to or slightly larger. Where am I? No, I'm in the wrong place. Silly me. I'm in the wrong place. There we go. We look for about XXZE, and we go down the table, and we look for a value that's equal to or slightly larger than 13464, but which happens to be, so that is bigger than this but smaller. So we find a section size that's equal to or slightly larger than the one we want, which is a 457 by 191 by 74, which has a value of 1460 times 10 to the power 3 millimeters cubed, and that's the section there which will adequately carry this load over here. Okay, now what happened there now? There we go. Okay, so people, that's how we do question number 2, that one over there. Okay, first find its z value, go down and go to the table and look for a value that's equal to or slightly larger than it, and that's the one we pick, and we state what its z elastic value is, and that's how we answer that one over there. Okay, so people, do the rest of them. You know, there's number 4, number 5, no, there's number 5, there's your beam like we did in applied mechanics and theory of structures. It says a timber beam having a rectangular section, that's D and that's B. It says determine the max bending stress. From here you draw the shear force diagram, you work out the reactions, you draw the shear force diagram, you draw the bending moment diagram, and then from the bending moment diagram you find your maximum bending moment, and that's your M. From M over I is equal to F over Y. So once you know your M, once you know your B and D, you can work out I, and once you know Y, you can work out Y from there, and from there you can work out the maximum stress the beam can carry. Okay, and what's Y? Y is equal to D over 2, which is 120 millimeters, and from there you determine F. You make F the subject of the formula from your M over I is equal to F over Y. So as I said earlier, you need to do more and more and more before you can actually apply the theory of elastic bending. I'm going to the next one. It says the figure below shows the cross section of that, spanning that. So that's L. It says find small w, and there's F. It says find the UDL, and there's the cross section. So what do you need to do? You need to work at Y top, Y bottom. You need to work at IXX, applying the parallel axis theorem. And once you got that, you can work at the maximum bending moment can carry, and I've given you, that's F over there, I've given you span, and from there it's a standard case. You can work at maximum bending moment can carry. From there you make F the subject of the formula, and then from there you can work at the maximum UDL the beam can carry, and it's 20.9 kilonewtons per meter. Don't mix up the units, get the units right, and then you sorted that, and I said derive a formula. I'll leave it up to you. And number 6, use your steel tables, find the bending moment diagram. I'll leave the rest up to you to figure out. But people, that's the exercises you need to do, and do them all for the theory of elastic bending. People, that's it about for the end of the teaching for the theory of elastic bending. Work through the videos, do all the problems I asked you to do. There's all the answers. And once you've done all the videos and do all of it and got the answers, then you should be able to answer any question I ask you under the theory of elastic bending. Okay, and I shall see you in the next video for the next and final topic in the theory of structures course, and that's deflection. I'll see you in the next video.